Okay, welcome. Today we are going to talk about the volt-second balance rule. So my name is Brian Modena and my colleague is Emmanuel Wambua. So welcome to East Academia, and please don't forget to subscribe. So the volt-second balance rule is given us, and it is stated as in equilibrium or steady state, the average inductor voltage VL is 0. So the mathematical expression is 1 over t integral from 0 to t VL dt is equals to 0. And this is nothing but the average of the inductor voltage VL. So we can derive the volt-second balance rule as follows. So we'll start from VL is given as L di over dt. Okay, in which case we can write VL over L is equals to di over dt. In a similar manner, we can just write VL over L dt is equals to di. Then integrating both sides over complete period, we are going to have I is given as VL over L integral from 0 to t dt. Okay? Then this is the initial value, and this being our final value. Thus, this I, we can break it into I as the final value, so we can have the final, that is the current at the period t, minus the initial, the current at 0, where we started, is given as 1 over L, integral of 0 to t, VL dt. Okay? Now, this inductor current, there are some assumptions that we're assuming here. That the first assumption is that the steady state conditions have been reached. So steady state conditions have been reached. Number 2, the inductor current. So inductor current rises and falls linearly. Okay? So with these basic assumptions that we've stated here, we can draw a waveform of the inductor current. That it starts from a minimum value. Okay? And it increases. It starts from a minimum value, and this is I at time 0, because in this case, t is 0. It reaches a maximum point, after which it falls linearly and reaches its final point. So this, I'll say it's I at the period t, and this time here t is equals to t. Okay? So during this period, the inductor is charging and is storing energy. And during this period, the inductor is discharging and giving out energy. However, looking at this diagram, the final and initial values are the same. Okay? They have the same magnitude. So therefore, IT minus I0 is going to be 0. So this expression then reduces to 0 is equals to 1 over L 0 to t of VL dt. Okay, so we can take this L this side. If you multiply, we're going to have 0 is equals to integral 0 to t of VL dt. Okay, an equivalent form of this expression we can divide by t on both sides. So you're going to have, this is nothing but 0, 1 over t, 0 to t, VL dt. So this is nothing but the volt-second balance rule, or inductor voltage second balance rule. So, diagrammatically, this is drawn as follows. So, we are going to have VL, and we're going to have our time t. Okay, so voltage times time is nothing but volt second, because this has a unit of voltage, this has a unit of seconds. So this is the volt second, this is also volt second. But as seen from this side, the total is going to be 0. Okay, so thank you for watching. Please don't forget to subscribe to East Academia, like, share, and click on the bell icon so as to get notifications when you upload new videos. Now, the applications of volt-second and balance rule will be done in subsequent videos, in which we are going to derive expressions for the transfer ratio of converters in both ideal cases and in cases of non-idealities. Okay, so thank you and keep watching.